Welcome to the pre-lab videos for experiments 3 and 4. In this video, we're going to focus on how we can learn about the acidic or basic functional groups present in our unknowns by studying the solubility of our compounds in aqueous solutions at various pHs. As you come into your solubility test during the experiment 3, it's important to remember that each of the unknowns will contain at least one of the functional groups listed here. Furthermore, it's important to remember that organic molecules with greater than 5 carbon atoms tend to have poor water solubility. So for instance, even these organic acids and bases, which contain polar carboxylic acids and amines, are not particularly soluble in water because they contain greater than 6 carbons. When you start out in your solubility tests, you're going to begin by exploring your compound in neutral water. You'll take a small portion of your unknown compound, add neutral water, and observe. If you observe a clear solution with no solid particulates that is a single layer, this indicates good solubility. I would expect then that your molecules have less than or equal to 5 carbon atoms and that they contain polar functional groups such as alcohols, amines, and carboxylic acids. For instance, take this triol, a small 3-carbon molecule with 3 alcohol functional groups. I would expect that to have exceptional water solubility. If you do not observe solubility of your compounds in neutral water, you can move on to aqueous solutions of different pHs to learn more about the molecule. For instance, we could use aqueous basic solutions such as hydroxide to determine whether or not we have acidic functional groups present. Let's take a look at how that would work. Consider the carboxylic acid, benzoic acid shown here. When treated with a strong base sodium hydroxide, we form a carboxylate anion and the conjugate acid water. Notice that the anion has charge. Relatively speaking, charged organic molecules have much better water solubility. So if I were to form this carboxylate anion, I would expect to observe a clear single layer solution, indicating that I have reacted and thus dissolved my molecule into the aqueous solution. When we're predicting or thinking about how an acid-base reaction will proceed, it's really helpful to remember our pKa's. So the pK of benzoic acid is about 4.5. And you could see that as benzoic acid reacts to form the carboxylate anion, we form the conjugate acid water, which has a pK of about 16. When we're validating that we expect this equilibrium to favor the products or go to the right, we can use the pKa's. You'll notice that we are starting with a species that's pKa is 4.5. And we're forming a conjugate acid with a much higher pKa. If we're moving from the lower pKa, representing the stronger acid, towards the higher pKa, or weaker acid, that's considered a favorable direction. And so for this process, I can expect the equilibrium to lie far to the right. For this reason, in basic conditions of sodium hydroxide, I would expect the majority of my carboxylic acid molecules to become deprotonated, and this would give them the water solubility I'm looking for. If your compounds are neither soluble in neutral nor basic solution, you'll want to explore acidic aqueous solution. If your molecule reacts in the presence of an aqueous acid, it's likely to be an organic amine. The amine is our basic functional group. It has this lone pair, which allows it to act as a proton acceptor. So if we consider the equilibrium shown, as the amine picks up a proton, it becomes an ammonium ion. This conjugate acid now has a charge and thus becomes soluble in water, which will give you the visual observation of a clear single layer solution. Again, we can validate that this is in fact a favorable equilibrium for the amine shown by looking at the pKa's. I'm starting with H3O+, which is representative of a strong inorganic acid. The pKa is quite low, indicating a strong acid, -1.5. As the reaction proceeds, the nitrogen picks up a proton and forms the conjugate acid with a pKa of about 11. Again, I'm going from a lower to a higher pK number, which indicates a favorable right-lying equilibrium. As you're looking at the list of unknowns, you're probably realizing that there are actually two functional groups that are acidic. We have both the carboxylic acid and the phenol. Is there a way we can distinguish them with our functional group tests? Yes. In the solubility test, we can not only use sodium hydroxide, but we can also explore a weaker base. And let's take a look at how that weaker base will let us differentiate the carboxylic acid from the phenol. As we've seen before, in the presence of hydroxide, we expect an extensive deprotonation of the carboxylic acid. If we switch to a weaker bicarbonate solution, I still can produce the carboxylate anion, and I would generate the conjugate acid carbonic acid. If I assess the equilibrium using our method from the previous slides, you'll see that I'm starting with an acid of a lower pK number and moving towards the acid with a higher pK number. So I am again using the stronger acid to form a weaker acid. This is thus a right-lying favorable equilibrium. So if my molecules contain carboxylic acid functional groups, I would expect to observe solubility when treated with aqueous bicarbonate. So again, looking for a fairly clear solution, single layer. By contrast, let's take a look at the phenol. In the presence of sodium hydroxide, the phenol will become deprotonated, forming a phenoxide anion. Charge, again, tells us that this will be water soluble. I form the conjugate acid water, and if I evaluate this equilibrium, I'll find that it does in fact favor the products. I'm going from the lower pKa to the higher pKa number. One of these things is not like the other. Our outlier reaction on this slide is going to be the reaction of the phenol with bicarbonate. What you'll notice is when we use bicarbonate in the presence of phenol to form a phenoxide anion, we would generate carbonic acid as the conjugate acid. In this case, the carbonic acid has a pKa of 6.4. When I compare this to the pKa 11 of the phenol, I could actually see that the carbonic acid is stronger than the phenol that I started with. Again, we always want to be moving from the lower pK number to the higher pK number. And so this is actually an equilibrium that does not favor the phenoxide. Instead, it favors the starting materials. So in the presence of the weaker base bicarbonate, phenols will not extensively deprotonate. And in the solubility test, you would not expect to see a clear solution formed if you have a phenol present. So with this information in hand, you're ready to evaluate the functional groups present in your molecules. A couple of caveats. If your compounds are soluble in neutral water right at the start, you don't need to carry out the other solubility tests. If you're soluble in neutral water because you're small and polar, you're likely to dissolve in all of the aqueous solutions. Instead, what could be more useful is to look at the pH of the neutral water before and after the dissolution of your material. The change in pH could help tell you if your unknown organic is an acid or a base. Lastly, if you prove to be insoluble in all of the aqueous solutions, it's most likely that you only have neutral functional groups, such as alcohols, aldehydes and ketones, or nitriles. And this is where infrared spectroscopy will actually allow you much better to focus in on one class of functional groups. So we'll see you this week in lab, where we'll start to narrow down this really extensive list of unknowns to a few possibilities that could nicely represent your unknown compounds. See you then.